Hi everyone, I'm Damiano Piovesan. I come from the University of Padua, and today we're going to talk about critical assessment of protein intrinsic disorder prediction. So intrinsic disorder proteins and intrinsic disorder regions are those proteins or regions which can exchange structural conformation very rapidly, or which lacks a lot of secondary structure elements. So this phenomenon is quite abundant in proteomes, in particular for high organisms. And for example, it's estimated that in human, at least 1/3 of the residues are actually intrinsically disordered. Looking at the structure, these structural features are easy to detect. For example, you can measure the accessible surface area per residue, and you clearly separate what is a globular protein and what is an intrinsically disordered region. Intrinsically disordered prediction has been effectively used in kappa-3, at least. Here I've reported a couple of methods which I'm aware used disorder prediction to improve or increase their performance. The first is ZooLab method, which used fold index predictor. And the second is Inga-Tosato, which used the mobility light predictor. And mobility light is quite conservative predictor, so it predicts very few positions as disordered, way less than 30% compared to other methods. Well, what is KIDE? KIDE have been published a couple of months ago in Nature Methods. The source code is available, the data set of the predictions. There are a lot of analysis in supplementary material, but interesting, you can also execute the full evaluation, and all the data are already provided within the CodeOcean capsule. So you have an environment which runs on the cloud and in which you can test, modify it, and see how the evaluation is performed. What is KIDE in short? What is the input and the output? The input is the protein sequence, and the output is the region definition and how we define the region. Basically, for each residue, we ask the predictor to provide probability of that residue of being disordered or ordered, and the classification of that position, because in some cases, some predictors just provide the probability. In some other cases, they provide just the binary classification, but also sometimes binary classification and the probabilities are not coherent. So they apply some post-processing to the binary classification in order, for example, to merge closed region and things like that. So the setting is quite different compared to other challenges. In KIDE, participants submit software and not predictions. And the software is executed on in-house on local servers by the assessors themselves. So this way you can not only evaluate the accuracy or the quality of the predictions, but you can also evaluate what are the technical aspects and things which are related to the execution and usability of the software. So intrinsic disorder prediction is not the first time it's been evaluated, but it was also a CASP challenge. It was a CASP challenge from 2002 to 2012. And then it was stopped because the lack of targets. And historically, the ground truth was defined by looking at missing residues in crystal structures or at mobile residues in NMR models. These two sources of information had a problem. So intrinsic disorder regions were quite short, and they covered only 10% of the residue, so less than what expected from the common knowledge. And most of the cases, these regions were at the NC termini of the sample. So in KIDE, the setting is a little bit different. So we also include missing and mobile residues, but we also include what are called secondary methods. So all those experimental techniques which are able to detect lack of structure, but in a non-directly, and that can be used also for extreme cases, for example, for fully disordered proteins. All this information or this knowledge comes from DISPROT, which is a database of manually curated evidence from the literature. And here are the results. So first we received 27 different software packages, many of them unpublished or published very recently. And they generated 43 different outputs, including both disorder or binding region inside disorder regions. And when you do this kind of exercise, when you have the kite setting, as I said, you can evaluate the technical aspect of this software. So what we noticed immediately was the different output format for all of them. Some of them are very large. They come with databases embedded. In many cases, you don't have control on the output path, or you have to rely on old or obsolete libraries. So they are also sometimes difficult to install. Well, we generate these baselines. Basically, the first idea is that whenever you have information from the PDB, in particular of information about observed residues in crystal structures, but you can infer that those positions are not disordered, and then you can simply project PDB information on your target sequence, or you can perform blast searches and choose different thresholds to say if it's you can transfer or not transfer observed position. You can also use HMM models, so generalize a little bit more the detection of the structure. The other idea is that disorder is less conserved compared to structures, and that's because you don't have evolutionary constraints on contacts, as in globular proteins. And the other idea is that since you know what is more or less the disorder content at the dataset or proteome level, you may want to simply assign 30%, for example, of the position as disordered and shuffle the entire data set and see how the method perform. So we have three different definitions of ground truth, starting from the DISPROT and PDB data. And the simplest one is what we call DISPROT. And simply we consider intrinsic disorder regions as annotated in DISPROT as positive labels, and the rest of the sequence as negative. Then we have the DISPROT PDB ground truth, in which we actually consider the positive as in the DISPROT ground truth. But for the negatives, we only consider those positions which are actually observed in the PDB. So negatives are only those residues which are three-dimensional structure. All the rest of the position here in white are excluded, both in the ground truth and from the predictions. While the third ground truth is DISPROT binding, and in this case, we simply consider binding regions as annotated by DISPROT. So the three ground truth are unbalanced in different ways. The less unbalanced is the DISPROT PDB. In total, you see, we have considered 646 proteins, majority of which come from eukaryotes, and the good representation of also other domains. So this is the result for the simple DISPROT ground truth. And you see that all the methods actually are better than the baselines. You see here the baselines with white columns. On the bottom, you also see the execution time. So you have the distribution of time necessary to produce one output. And you see that the difference is quite large between different methods. There are order of magnitudes of difference, and because some of the methods exploit evolutionary information, for example, performing a blast search against the database of sequences. On the other hand, you see that the Fmax is not that high. So apparently predicting disorder as defined in this protein is not that easy. But the results are quite different when you consider the disparate PDB ground truth. In this case, baselines are not, sometimes they are better than the predictors. Top performing predictors actually extensively used evolutionary information and evolutionary information, and they are slower indeed. And the fact that this baseline is higher compared to the top methods is just because the PDB observed baseline cannot make false positive by definition. So it's somehow an artifact compared to the rest of the methods. Well, for disparate binding, the situation is even worse. Well, actually, methods are better than the baselines, but the overall Fmax is very, very low. On the other hand, we can consider here that defining negatives for binding is very difficult. And at the time, disparate just started to annotate binding regions. So at the time, disparate was extremely incomplete compared to what is now. So we hope that second edition, this situation will change drastically. Another change was the evaluation of fully disordered proteins. And to define a fully disordered protein, we simply consider if a predictor predicted at least 95% of the residues as disordered. In this case, the idea is that you don't evaluate the position of the regions, but instead you see if the predictor is able to discriminate between fully disordered and not fully disordered proteins. Here you see the table representing best methods based on the F-score, F1 score. And here you see the amount of predicted disorder residues for each method. And you see that the ranking is not simply the sort based on the amount of predicted disorder, but instead correctly identify which are the methods which can discriminate correctly these two classes of proteins. So in conclusion, novel predictors outperform old ones. Evolutionary information is useful, at least for the disparate PDB dataset output. Disordered binding regions are difficult to predict, and a number of disorder predictors are difficult to use due to configuration dependencies and all generating different output format. And disparate as a ground truth, we can safely say that it's better than simple PDB. In disparate, you have multiple complementary experimental techniques, not just missing residues. Regions are longer and functional. You have fully disordered proteins, and the dataset is larger. So we're about to run the second round of guide, and the deadline to submit the software is the 1st of April, 2022, so 1 year from now. And there is a phase, about 1 month and a half, in which we support the submitters to, or at least they support us to install the software in our machines. So there is this lag phase in which we are in close contacts to make this software working. Preliminary result will be published in July and final result in December. The idea is to get in sync with CASP, and the result will be published 1 year later. So in second edition, we will also add a couple of new sub-challenges. So we will split the binding. We'll consider the full binding as before, but also subclasses like protein binding and nucleic acid binding. And also we would like to add the linker prediction as a challenge, because linkers are very abundant in this protein, and they are likely to to have different sequence features compared to binary regions. They, for example, should be less conserved. But with that, I finish. I would like to thank the organizers, guide predictors, all the dispute curators, and of course, my laboratory and Silvio Tosatti in particular. Thank you for your attention.